Welcome back. This is the continuation of section 11.7 strategy of testing the series. We have seen few examples where we applied different tests, test for divergence in one problem, limit comparison test in the next problem, and we saw integral test. Then in this one, in this example, clearly we have that negative 1 to the power n part. So that means the series is an alternating series. The series is an alternating series. So the obvious test would be the alternating series test. Apply alternating series test. Alternating series test has got some requirements. So we have to show that bn plus 1 is less than or equal to bn, which means that the sequence is decreasing, and then the limit of the nth term equal to 0. So we have to show bn plus 1 less than or equal to bn, where bn is the absolute value of an, the positive part of an. And the second one we need to establish is that limit as n approaching infinity of bn equal to 0. So let's try to do the first part. So because the numerator is involving n to the power of something, so it's better we go for the relating function. So consider the relating function. Is f of x equal to x cube divided by x to the power 4 plus 1. So what is the derivative? Derivative is the quotient rule. We'll apply the quotient rule. It is denominator times derivative of numerator minus numerator times derivative of denominator divided by denominator square. So we get 3x to the power 6 plus 3x square minus 4x to the power 6 divided by x to the power 4 plus 1 the whole square. So f prime x, first notice that 3x square, we get 3x square. Then we can combine these two. That will give us minus x to the power 6 divided by x to the power 4 plus 1 the whole square. X square can be common factored out. So it is 3 minus x to the power 4 divided by x to the power 4 plus 1 the whole square. The denominator is always positive. So f prime x is negative when the numerator is negative. But this part is always positive. So it is negative only when 3 minus x to the power 4 is less than 0, or when x to the power 4 is more than 3, or x is more than 4th root of 3. Fourth root of 3 is approximately 1.3. So whenever x exceeds 1.3, the function would be decreasing. Or we can say f of x is decreasing on the interval 2 through infinity. It's enough if it is eventually decreasing, right? So this means that because it is a relating function, it actually applies to this condition. So Bn plus 1, so condition 1 is proved in this case. So condition 1, Bn plus 1 is less than or equal to Bn is proved. We're proving it for n more than or equal to 2, which is fine. Then the next part is condition 2, which is easy to do. So we are going to do limit as n approaching infinity of Bn. And we are looking at this step now. So we've already established condition 1. We are now proving condition 2. Limit as n approaching infinity without the negative 1 to the power n part, it's n cubed divided by n to the power 4 plus 1. So if you divide the numerator and the denominator by n to the power 4, it will be limit as n approaching infinity. N cube over n to the power 4. So that will give us 1 over n. And n to the power 4 over n to the power 4, which is 1, plus 1 over n to the power 4. So this is 0. This is 0 as well. It is 0 over 1, which is equal to 0. Thus, condition 2 is also established. The condition 2 is proved. Therefore, condition 1 and condition 2 are satisfied. So what is the conclusion to the problem? By alternating series test, a series, given series sigma, negative 1 to the power n, n cubed divided by n to the power 4 plus 1 converges by alternating series test. Let's take the next example. Sigma k varying from 1 to infinity, 2 to the power k over factorial k. Because of the presence of factorial in the problem tells us that we have to apply ratio test. So let's start with step 1. What test to apply? Apply ratio test. So we will take the ratio of the an plus 1 the term over anth term. A sub n plus 1 over a sub n. So let's write an, which is 2 to the power n over n factorial. An plus 1 is 2 to the power n plus 1 over n plus 1 factorial. And the ratio an plus 1 over an. Here we don't even have to mention about absolute value because the terms are all positive terms. So it is 2n plus 1 over n plus 1 factorial divided by an. So take the reciprocal and multiply n factorial over 2 to the power n. So we get 2 to the power n plus 1 over 2 to the power n. We will reduce n factorial over n plus 1 factorial. 2 to the power n, 2 to the power n plus 1 on top, that will give us 2 on the numerator. Then writing this n plus 1 factorial as n factorial times n plus 1, which trick we normally do, factorial n cancel out. So you are left with numerator 2, denominator is just n plus 1. Now, limit as n approaching infinity of absolute an plus 1 over an, the ratio of a sub n plus 1 over a sub n. We don't have to do the absolute value, but we will stick to the rule, the ratio test. Limit is n approaching infinity of absolute 2 over n plus 1. So it is numerator is a constant, denominator is a very big number. So it becomes 0. L is less than 1. So this is your conclusion. By ratio test, given series sigma 2 to the power k over k factorial, k varying from 1 to infinity, is convergent, is absolutely convergent and hence converge. So here they've used the index equal to k, but whether it is 2 to the n over n factorial or 2 to the k over k factorial, it's all the same. Let's take example 6. Test the convergence of sigma 1 over 2 plus 3 to the power n. So let's consider maybe before this one, I think a regular comparison test would work. So to do the comparison test, we have to get the right-hand side series, which is a known series, either a P series or a geometric series. So we will look at the denominator of the given series, which is 2 plus 3 to the power n. So I can say 2 plus 3 to the power n is more than 3 to the power n, one of the two terms. So if I take the reciprocal, then inequality will get reversed. 1 over 2 plus 3 to the n is less than 1 over 3 to the power n. So it looks like an. The left-hand side is the nth term, given nth term of the given series. So we have something like this now, an less than bn. Then what can you say about sigma bn? What is the series sigma bn, which is sigma 1 over 3 to the power n? We are able to write this as sigma a times r to the n minus 1. So we can write this as 1 over 3 times 1 over 3 to the power n minus 1, which means that this is a and r is 1/3. So this is a geometric series with starting term 1/3 and common ratio, absolute value of the common ratio is less than 1, and hence it's a convergent series. So you are comparing the given series with the convergent series, convergent geometric series. And we also have this condition an less than bn for every n. And this is true for every n. Therefore, your conclusion would be by comparison test, given series sigma 1 over 2 plus 3 to the power n converges. I have shown some problems in this in my video from the suggested exercise. I have shown problem number 1 in the video, and 8. I've done 7. These problems are done in the section videos. Please refer to the section videos. Hope these videos help.